Yeah, hi. So we will start on the talk now. Myself, Leena Bora. I am an application developer with Equal Expert. It's been more than 3 years that I'm with Equal Expert. Prior to that, I was working with ThoughtWorks, Cognizant, and Synchron. That's about me.
Yeah, and I'm Christian Huyer. I'm developing software for more than 30 years now. It's been the thing I've been doing most of my life, apart from breathing and maybe sleeping. And I think it's fun and it's getting more interesting year by year. And now let's start with functional programming. So I'll start with the history of functional programming. So this is the first guy that's important for the history. He came up with the lambda calculus on which the functional programming is based. So that's what he created. He also created the type system on which most of the functional programming languages of today are based. Some modern functional programming languages like Scala, they significantly extend this type system by combining the abilities of programming languages like Java to have a strongly typed system with the lambda type calculus. This guy, John McCarthy, is also very important for the history of functional programming. He often is coined as the father of functional programming because he turned the lambda calculus into a programming language, basically the first proper functional programming language, Lisp. And Lisp is seen as the birth of functional programming, and that was in 1958. When you think of it, that's actually quite old already. It's older than integrated circuits. It's older than CPUs. And it's also older as the other two predominant programming paradigms. It's older than structured programming, and it's older than object-oriented programming. But it hasn't been very popular for quite some time. It's only really gaining popularity recently. And then there's this guy, John Backus. His most well-known works, the BNF grammar for describing syntaxes of programming languages, and Fortran are actually not very closely related to functional programming. But effectively, in the end, he excused for his work on Fortran, and he asks, can we liberate programming from the von Neumann style, which is basically based on mutation of things, and can we get away from this? This is a nice quote which I found on Twitter, and it already talks about why functional programming is gaining popularity recently. It tells you that it's not about functional programming is better because it supports concurrency, but it's supporting concurrency because it's better. So much of the talk will of course be about why functional programming is the better paradigm. That's a sketch of the most important milestones. So we already had lambda calculus, we had Lisp, and we have Algol 60, which is not really a functional programming language, but it brought programming a huge leap forward. Most programming languages that we look at today have their roots in Algol 60, indirectly, usually via C, and today also via Java. A lot of things are going on the Java virtual machine. And if you're a Microsoft fan and say, oh no, it's .NET, that's just the virtual machine modified so much that you don't have the priorities to Sun or Oracle. Then there are a few more steps. I think most notably Haskell, which probably is the cleanest implementation of functional programming done so far. And if we have time at the end after the main talk, we might be showing a few listings, but we'll have to see if we have time for that. If we do, there will be quicksort in Haskell. And then there's Clojure, which brought Lisp, which probably is the most popular dialect of functional programming, onto the virtual machines, onto .NET and onto the Java virtual machine. And a very important milestone also is Java 8. It's of course not a milestone for the evolution of functional programming as such. There's nothing new added to functional programming by Java 8. And if you already know a bit about Haskell or Scheme or Lisp or F# or Scala or Groovy or even Ruby, and about the functional programming capabilities of these languages, you will actually look down on Java 8 and say it's compared to what these languages can, Java 8 is a joke. But we have to keep in mind that Java 8 is still the most popular programming language, and what Java 8 contributes is it makes elements of functional programming accessible to a much wider audience. And I think that's also an important contribution. It's not contributing to the evolution of functional programming, but it's contributing to the popularity of functional programming. That guy with the fish in his hand is Gordon Moore. What is he known for? Moore's Law, yeah, that you can read on the slide. But what else is he known for? Fishing? He's one of the co-founders of Intel. And he basically is the father of the microprocessor. He was born in 1929. And he coined the phrase of the Moore's Law, where we say the number of transistors doubles approximately every 18 months. Usually, if we just quote it like this, we say 18 months. Originally, he said 1 year. Later, 10 years later, he said 2 years. So we take the average, say 18 months. And that has, over a long period, led to more gigahertz in our CPUs. But for how long? Here, you can see an evolution of microprocessors until like 2008. And that's about the number of transistors. So you can see how Moore's Law holds true. This is another diagram, basically showing the same thing. But this diagram looks a bit strange, isn't it? There's no line. There's a break here. So Moore's Law held true for 3 or 4 decades, and then bang, something happened. What exactly has happened? CPU development has hit physical limits. Moore's Law is no longer holding true in the same way as before. The gigahertz race has come to an end. When I purchased my computer, well, an old computer now, but a new computer back then in 2003, it already had 2.6 gigahertz. And it was not the fastest CPU available. And what are the fastest CPUs today? It's still around 2.6, 2.8, maybe 3 gigahertz. So for more than 10 years now, the gigahertz race has come to a halt. The transistors are still increasing, but it's no longer possible to use that increase in the number of transistors for increasing the clock speed. It's no longer possible. But we see something else is increasing. If you look at this, 1 was the number of cores. Now, the clock speed is suddenly no longer increasing, but therefore the number of cores is going up. Which means CPUs are still getting faster, but suddenly we have to change the way how we develop software as software developers if we want to utilize the additional speed. This guy is Jim Amdahl, and he came up with Amdahl's law, which tells us about parallelization. This is Amdahl's law. I'll not go into the details of the formula. They're just there for reference, or if you want to read it, you can read it up here. But what it basically says is that if you want to utilize a multi-core system or a multi-CPU system or a cluster, then you can only do so effectively if the amount of code which you can run in parallel is high. If the amount of code which you can run in parallel is low, and a lot of your code is running sequentially, then you can add as many cores as you want. It's not helping much. We really need software where the amount of code which you can run in parallel is as high as possible. So here you see, if you have code where you can run 50% in parallel, then adding cores will at max give you twice the speed of the original program. The speed up will be at max twice. If you have 95% of code that can run in parallel, the speed up will be at max 20, not more. You could have 100 cores, you could have 1,000 cores. The speed up you get if 95% of the code can run in parallel will still just be 20. So in order to utilize multi-core CPUs beyond this, we have to come up with parallelism possibilities in our software, and that's a challenge for us programmers, where more than 95% of the code can be run in parallel. This guy is Gustafson. He came up with a similar law. It's a bit more optimistic. The graph looks like this, but effectively it still says that you have to code for parallelism if you want to utilize multi-core CPUs. To run fast and utilize this, we need parallelism and avoid race conditions. That's the reference for this part. Next part is Lena.
So what could be the best start other than this, right? So what is the functional programming? Is it some language like you have Scala, Haskell, Clojure, Java 8? Is it some language, or is it some framework like you have the Play, Scalatra? Or is it some conceptual tool like you have the TDD or BDD? So is it some language? Is it some framework? Is it some tool, or is it something else? What it is? Sorry? Yeah. So in other terms, I would say it's a programming paradigm. Okay. So when you say it's a programming paradigm, what do you understand by it? What is programming paradigm? So programming paradigm means the way you structure or organize your program and its elements. For example, object-oriented is a programming paradigm. So if you code in any object-oriented language, it could be Java, C#, Smalltalk, how you structure your program? Basically, you have the classes, you have the objects, and objects collaborate with each other, right? This is the high-level structure of any object-oriented program. So if we are saying that it's a programming paradigm, then how do we structure our functional program? And if in one line I have to answer you, then I'll say it's all about functions. Then you will say, okay, that's fine, then how is it different than other language? Because we have functions everywhere, right? We have functions in Python, C, C++, everywhere. So what is so special about it here? So in order to understand that, we are going to do one exercise. What we are going to do is, we are going to switch off the computer science stream from our brain for a while, and we are going to go back into the mathematics. The reason why we are doing this exercise, because as Christian mentioned, the functional programming has its deep roots into the mathematics. So don't be scared with the word mathematics, because as I mentioned, we are not going to learn anything new. We are just going to revise what we already know. So what is that? Just think from the mathematical perspective, no computer science knowledge is required. What is that? Right, so that's a mathematical function or a mathematical equation, or you can call it as a mathematical expression, right? So the way now I'm going to do is, I'm going to slide over some of the points and you're just going to say whether it's true or false. Okay? F of 2 equals to 7. True, simple one. The value of x will never change inside a mathematical function, will it? Is it changing? The value of 2 is changing? No. So that is also true, right? Same input, same output. If I call f of 2 100 times, will I get some other output other than 7? No, right? So that means that is also true. Assume that this piece of expression is part of your bigger mathematical algorithm. So if I evaluate this particular expression, will it have some negative impact or impact on your algorithm? No, right? So that is also true. Assume that you have f of 2 at multiple places in your algorithm. If you replace that f of 2 call with its result, which is 7, will the final output of your algorithm, will that change? No, right? So that is also true. So these are the few characteristics of mathematical functions. And if I have to summarize those, then I would say for given any mathematical equation, if you call it with some input, same input, you're always going to get the same output. No matter how many times you call, no matter when you call, and it will not have impact on other part of algorithm. I'll just repeat it since it is very important. Same input, same output, no matter how many times you call or when you call, and it will not have impact on other part of algorithm, right? So due to this characteristic, for any mathematical equation, we are able to plot a graph. If x-axis denotes the input and the y-axis denotes the output, we are able to plot a graph, right? As I said, the functional programming has its deep roots into the mathematics. For functional programming, mathematics is a role model or a superhero. So whatever that mathematics does, functional programming has to do it. So it says if in mathematical function, it follows these two rules. If it follows those two rules, same input, same output, right? So whenever I'm going to write these functions, right, even I'm going to follow these two rules. In mathematical literature, we call it as an expression, mathematical function. And in computer science literature, we call it as a pure function. Function that follows these two rules, same input, same output, right? So that's the example. That is the same expression. Now I have written it in a computer science, right? And let's see if it follows those two rules. I call it with the same input, and now I'm getting the same output, right? And that's why it follows those two mathematical rules, and it is called as a pure function. In the beginning of this year, I have made a New Year resolution that every month when I'm going to get my salary, I'm going to save some part of it. Otherwise, I used to just spend everything, right? And I have written a simple program to simulate the banking system for it. So if you look at that credit method, what it is doing is, it's a simple method. It's just taking the amount to be saved or credited in bank, and just it returns you a new balance, right? So in the first month, initially I have the balance of 100 rupees. I'm not very rich, my balance is 100 rupees, okay? So first month when I got my salary, I have credited the 500 rupees in bank, and now my balance is 600 rupees. Next month, again when I got my salary, so instead of spending the money on shopping, I again decided to save it, and now my balance is 1100, right? So Lena, as a bank user or an end user, is now very happy because now she is able to save some money. Lena, as an object-oriented programmer, is also very happy because whatever program she has written is working as expected. But Lena, as a functional programmer, is not happy with this program. Can you spot why?
The value of balance changes with time.
Exactly, right? So So we said in functional programming, we write the pure function. That means same input, same output. So here I am getting the 500, I am getting the output as 600. Next time I am giving it as a 500 and now I am getting it as a 1100. Then you will say, just to satisfy those crazy rules of mathematics, should it not credit amount into my account? No, right? That's not acceptable, and that's the last thing I would want to happen as a bank user, right? So whenever we are going to rewrite this program in a functional style, we have to fulfill two requirements. Requirement number one, that the behavior should be intact. And what is the behavior? Whenever I'm crediting the amount, it should give me the new balance, right? And the second requirement is that the credit method should be a pure method. That is, same input, same output. So we are going to rewrite the same program in a functional style. To write a code in a functional style, you really don't need a functional language, right? You can still write the code in a functional style with your existing language, of course, to some extent. So I have written the same program in a functional style in Java, okay? So that's my modified code, and let's see if it fulfills my two requirements. The primary requirement is it should persist the behavior. So initially I have the balance 100 rupees. Next time, when I'm crediting the 500, I'm getting the balance as 600, okay? Next month, when I again get this salary, I'm crediting the amount 500, and now I'm getting the balance as 1100. So my first requirement is fulfilled, that my behavior is intact, right? Let's see if it fulfills my second requirement, that the credit function should be a pure function. So when I do the account.credit, same as above, which is highlighted one, I am getting the same output. So both the requirements are fulfilled, and Lena, as a functional programmer, is also now very happy. Okay? So if I go back to my earlier slide, right, and I said that credit method is not a pure method, right? That means it is an impure method. What do you think, that what has caused the impurity in it? Precisely. Because the output of credit method is dependent on some external factor. And that external factor is a balance field, right? And that balance field is a mutable field. Mutable is that can change anytime, right? So output of that credit method is dependent on that. And that's why it has made it impure. Right? So if I have to make a generalized statement about this situation or a scenario, then I would say having a global mutable state in your program can make your function impure, right? So here balance field is causing the impurity, and things which causes the impurity in computer science are called as the side effects, right? So we have just seen one thing, that is having a global mutable state can cause the impurity in your program or a side effect in your program. So there could be many other reasons which can cause these side effects or make your function impure, right? So modifying the input value. You remember our first mathematical slide where we said the value of x will not change inside the function. So if you do that, then that will make your function impure, or that will cause the side effect. If you are throwing an exception from your function, then it will make your function impure. If you are making a database call or if you are making any I/O calls, or if you are making some file operations, then that function will become impure, or that will cause as a side effect, as they say in computer science or in functional programming. If your function is talking to some external service, if it is making some web service call, then it will introduce the side effect, right? So we say that in functional programming, we write the pure functions. And if we do any of this thing, then that will cause the side effect, right? So will there be any project in real world which do not talk to the database, or do not make a web service call, or do not throw an exception, right? So there won't be any real world project. So does that mean functional programming cannot be used for a real world project? So answer is, of course it can be used, and our answer lies in this diagram. How you design your functional programming application. So at the heart of your applications, you have the pure functions, right? At the core, you have all the pure functions. And on top of that, you build a very thin layer where you have the functions, impure functions. That means there you can make a database call, or I/O calls, or exception. We are not going to go into the details of this design, because it itself is a separate topic of discussion. That's A. And B, in order to understand that, we need to have the understanding of some advanced concepts like monoids, functors, applicative. That's why we are not going to do that. The reason why I have shown you this diagram, because I didn't want to leave you in a complete confused state where you're thinking, okay, if I'm doing the functional programming, that means I cannot make a database call. I cannot make a web service call. Of course you can do it. You have to design your application like this, and there are techniques to do that. You have to use the monoids to write the impure functions in your program. So you will say, that's fine. I mean, mathematics follows or copies everything. Functional programming copies everything from the mathematics, right? But does it just blindly copies, or does it really have some benefit? So we are going to see why I should write a pure function. So when first time I heard about it, it felt like a constraint to me. Oh my God, it's so difficult, right? If I introduce the global immutability, it's so simple for me. So let's see why pure function. By the way, is that a pure function? Yes, right? Because the same input, same output. And it doesn't have any side effects, which we have just seen in earlier slide. Before even going into the details of why pure functions, we are going to understand one term, and that's referential transparency. Sometimes I feel that these functional scientists are very innovative or very expert when it comes to giving a name. I feel they give very fancy names to simple things. When I first heard about this referential transparency, I was like, oh, what's that? That sounds something very complicated or out of the box concept. But to my surprise, it wasn't like that. So let's understand what does that mean. Assume that you have a program, big program, right? And you have this square of 5 call at multiple places, right? If you replace that square of 5 call with its value, which is 25. Assume that you are hard coding the 25 everywhere instead of square of 5. Will the final behavior or the final output of your call, will that change? It won't change, right? That's the referential transparency. Okay, in a program, if you replace the expression with its result everywhere, and if it is not changing the final output of your program, then that expression is called as a referentially transparent expression. To understand this further, we are going to go back to our same example. Right? So here are these two calls, account.credit 500 and account.credit 500. Can I replace this two call with the value 600? Will that change will it change my output then if I replace that with the 600? It will, right? Because First time when I call it, answer is 600. Next time when I call it, answer is 1100. That means I cannot replace this, right? And that means if I cannot replace its call with its result, then that means this function is not expression, is not a referential transparent expression.
Yeah, we will repeat the questions.
Okay, so we were looking at the referential transparency. And we said that square of 5 call is a referentially transparent expression because we can replace that. Function, so any function is called as a pure function when it is a referentially transparent. So square function is called as a pure function because square of 5 is a referentially transparent expression. Okay, so that's about the referential transparency, and now we will get into the serious business where we will see what are the benefits of pure functions. So we have seen the main characteristics of pure function is same input, same output. So for that, then compiler can do a trick for us, right? So when it evaluates some function, then it can cache that result. So next time when it sees the same function call with the same input, it will say, oh wait, that's a pure function, then why should I re-evaluate it? Because I have already evaluated it and I already have the result. So let me reuse that result. That means it can memorize or memoize the result, and that's the memoization. So it can do such performance improvement or optimization trick for us. That's about the memoization. Execution order can be rearranged. Assume that you are writing a tax calculating system and you have these two functions, x, calculate maybe LBT for a year, and you have calculate income tax for a year. And you finally return the total tax which needs to be paid. Assume that these two functions are pure functions, calculate LBT and the calculate income tax. That means they are not dependent on any external factor. That can run independently. And here these two functions are also not dependent on each other. So when compiler executes our program and when it reaches to this point, it says, oh wait, instead of executing that function first, what I'll do is I will execute this function first, because in order to execute the second function, whatever is needed, I already have it in my register. So I can make such optimization and then I will evaluate this. So you see, compiler is able to rearrange the execution order, and that's possible with the pure functions because they are not dependent on some external factor. So that's one of the benefits. Local reasoning. Again, a very, very important point regarding the pure function. To understand that, again, I'll go back to our favorite example. Assume that I have shown you this slide and I have just hidden this line from you. And if I ask you, now since you know what that credit method is doing, and if I'm calling the credit method with the 500, will you able to tell me the output of this function? This call is already there, but I have not shown you. If I've kept it hidden from you, will you able to tell me what is the output of it, or will you able to predict it? No, right? Because the output of this call, it depends on the history. What has happened earlier. That means you cannot predict the result of pure function, or that means you cannot locally reason about it. So for impure function, the major problem is you cannot locally reason about it. It makes your system very hard to understand, because in order to understand it, you need the whole lot of context, what that program is doing. But with a pure function, which is I said this is a pure function. At any moment, if I tell you square of 10, tell me what will be the output of program. Will you able to tell me? Right, that's possible, because in pure function, you don't need the whole external context to understand how it will behave or what will be the output of this function. That means you can locally reason about the function. Last thing, and I think the most important point, as Christian also has pointed in his introduction talk, that the parallel execution. Nowadays, there's so much revolution is happening on the hardware. You have the multiple cores or multiple processors on your laptop, as well as on your mobile. You have the multiple core. But in order to leverage the power of that hardware, your program should be rewritten like that, right? And pure functions help there. How? Because pure functions can run in isolation, independently. They do not depend on external world. So if you have the multiple pure functions, they can be run parallelly on each core. And that's why it helps with the parallelization. Now let's see what is the definition of the functional programming. Functional programming is so called because program consists of pure functions and functions. The function is deliberately written in a small font because you want to avoid it as much as possible, and there are different techniques to do that, right? That's the definition. If you compare today's session with your first object-oriented session, right? There, first thing you might have learned about was about the objects, right? Because that is the heart or the backbone of object-oriented programming. Here, the first thing you learned about is about the pure functions, because pure functions are backbone or the heart of your functional programming paradigm. There, the next thing you might have learned about could be the inheritance, polymorphism, abstraction. We are going to do the same thing. Let's see what functional programming has to offer now. Okay? So, are there any questions?
Having that parallel execution, I mean, if I have like multiple pure functions, so who takes the responsibility to run it in parallel? Is it the compiler or?
So that's a very good question, right? Who does it? So compiler is not intelligent enough. He doesn't know what to run it in a parallel. So we have to tell to the program that these are my functions, run parallelly. But it provides the ecosystem or a very simple way where we can do such parallelization. Since we write the pure function, so it provides some language construct which helps us to write the parallel. Because compiler is not, it cannot read your mind basically. It doesn't know what to run parallelly and what not to run parallelly. Okay? Yeah.
Get from the function programming if compiler itself not able to understand how to process the parallelly, because non-function programming like Java also provides the facility to the threads that we can run the programs in the parallel. So what extra features of function programming provides?
So that is so if you overall ask me as what functional programming has to offer, we have just seen the one parallelism, right? So as I told you, so in the interest of time, I'm not really able to show you how we do the parallelism because it itself is a separate topic of discussion, trust me. So in order to again understand that, we need to pick up some particular language, then take the example and let's see how that needs to be done. But yeah, as I told you, it provides the ecosystem or a language construct which helps us to write the parallel code. It's very simple, believe me. Last week I was, yeah.
Maybe I can provide you a short answer for that. Is in case of normal imperative programs, what you do is you have a global state and you modify that. Now, of course, you can do all the parallelism you want, but managing that global state is hard. And functional programming actually tells you that you don't need that global state. You can use parallel functions, you can use local state or something like that. So if you are not having mutability, it is very easy to actually do parallelism in that case.
To add to it, you can see, even though you may seem like you are spanning your program into multiple threads and it might be visually running parallelly, but internally processor is handling one thread at a time. So that is in fact not internally parallel if you don't have multiple cores.
If I may also add something to the answer. It's not entirely true that there are no compilers or no environments that do not do automated parallelism. There are such environments. And they are even there for non-functional programming languages. For example, there are C compilers, like the C compiler from Parallels C, which automatically will execute parts of the code in parallel. But one of the things that you have to do for that is you have to use special pragmas or special annotations in C in order to help the compiler to understand which call trees can be run in parallel. And what is the problem if you run things in parallel? It's side effects, it's impure functions. So usually what you do, and the same thing is actually even also true for GCC. If you program in C, you mark functions as pure, which tells the compiler can use its other knowledge about the static analysis of the code that it performs while compiling the code to decide which parts of the program maybe I can run in parallel. And such environments exist. And also, as Lena pointed out, even if you do it manually, it's not always about whether my environment actually automatically does run things in parallel or whether I do it manually. If you do parallel programming in Java and you do the threads in Java, you still have the problem, what do you do about your race conditions? And the point about functional programming is avoiding these race conditions in order to enable that you have functional programming without, that you have parallel programming without bugs. That's the key point. Does this answer your question? Yeah?
I ask you, so what is the difference between functional programming and event-based programming that we usually see in browser or Node.js?
The question was, what is the difference between functional programming and event-based programming? I think it's not a valid question to ask. No, not in the sense that you've asked the wrong question. But it's like asking. I can't come up with an example. But functional programming and event-based programming are different views of how to slice the cake of programming. You can do functional programming and event-based programming at the same time, and you can do functional programming without event-based programming, and you can do event-based programming without functional programming. They are like very different topics, how you slice the set. Yeah, so therefore, you can't really meaningfully talk about the difference. You can use both concepts at the same time. It's possible.
We have seen the advantages of the immutability which it offers. So there is also one of the ways in which, in functional programming, we can create the mutable objects as well. So what are the ideal scenarios and why this provision is given in the functional programming to create these kind of mutable objects also?
Okay, I'll repeat the question. I think you will just answer it, right?
Yeah.
So the question is, now in functional programming, in many of these languages, you also have a facility to create mutable objects. The question is, so why is it there and what's the purpose? Is this your question?
Yeah. So you are partially correct that the functional programming languages offers you the mutability, right? So if you take the Haskell, right? Haskell is a pure functional language. In true sense, it's a functional language that doesn't offer the immutability. But Scala, right, which is a multi-paradigm language, that means it is an object-oriented language. It's a Functional programming language, it's an imperative language, it's a declarative language. In order to support the multiple paradigm, they have to support the mutability. That's done. Over to Christian. Do you need this?
No, it's working. I made it working again.
Okay.
So next part of the talk will be about higher order functions. Yeah? Okay.
Go back to this example. The account example that.
The account example.
Yes.
This one.
Okay. So basically, if you say that if it's a pure functional programming language, right? So here the thing is like what you mentioned was that if it's like memorization, like if the function has been executed, right, the value is being memorized or compiled, stored somewhere, and once we call the same function again, it returns the same value. So if I take that example, right, so if in this example, right, so every time if you call, okay, so you are calling on the second one, right? Okay, I'm sorry, that's fine.
I think maybe we should point out where his confusion came from. Yeah. So when you're purely functional, you can't change the value.
Yeah. So what we are doing here actually, right? In the earlier program, we knew that the balance was causing the impurity, or balance was causing the side effect, right? In order to remove that side effect, what we have done that we have composed that side effect into the return value account, and that solved the problem. Okay.
So whenever you have a side effect, you create a new object.
That's one of the ways. There are many other ways because there are many other types of side effects. And this is one of the way you avoid the side effect.
Okay, next part will be about higher order functions. This is where functional programming and object-oriented programming meet and intersect, and where they actually in some way tell you exactly the same thing, and we'll see. And I think this is also an important message that functional programming and object-oriented programming are not mutually exclusive. Actually, this is the part where they intersect very strongly. And I think it's very important for me to give you that message because I guess just because of the tradition and the evolution of programming, most of us will probably have a very strong object-oriented background. And when you understand these parts of functional programming, then your migration and extension into functional programming will be much easier. Because you see that a lot of things about functional programming, they have very fancy names, but they're actually very simple, and many of them you even already know. And also about the pure functions, if you look at APIs like the Java API, as a rule of thumb, if the function is static, it's probably pure. It is not guaranteed to be like that. Yeah, but as you know, in Java, we try to avoid static fields. If we have fields, we put them in objects. So there's a high chance, if you have a static method, that it's a method without side effects, and it's pure. And if you look at a class like math in the Java API, like Java-lang math, all the functions there, they're static. They don't modify the state of the math class. They're pure functions. So you already have pure functions in your APIs. You just need to discover them. And we'll also have examples where we see where in the Java API things are not pure, and that has actually put programmers into a lot of trouble. And this API would never be designed the same way again with our today's knowledge. But let's go to higher order functions. So in order to understand higher order functions, I first explain what is the opposite, the first order function. All the functions we've seen so far on the slides were first order functions. These are normal functions. Higher order functions are a bit special. Higher order functions have another function which they take as an argument or which they return. Now, how can you actually take a function as an argument, or how can you return a function? If you know OO, don't worry, you've been doing that all the time. and I'll show you how and why. I'll also tell you about the workarounds if the higher order functions as a syntax construct in the language are not available, what you can do. For example, if you program in C or if you program in Java, you actually do not really have higher order functions in the syntax of the language. But you can still use higher order functions. There are workarounds, and these workarounds are probably well known to you. If you know C, you probably know function pointers. If you have a function that takes a function pointer as an argument, or if you have a function that returns a function pointer in C, what you have is a higher order function. Or in Java, if you have an interface which has just one element, one method, like, for example, action listener, and then you have another method like add action listener, which takes an object that implements that interface as an argument. What add action listener is, it is a higher order function. And if you look at it a bit less strictly, you could also say if you have something like window listener. We all know window listener has not one method, it has multiple methods, but it's a set of methods. And a set of methods you can translate to a list of methods or functions you can translate as multiple functions. Yeah, that's also a higher order function. If you have to take a function that takes multiple other functions as an argument, that's a higher order function. Yeah?
Pass by pointer or return by pointer, our function. So why we don't call C as a functional language altogether?
The reason why we do not call C a functional programming language is the predominant paradigm, how you program in C, is with side effects. And also, there are certain things which you would expect of a functional programming language, which we will see throughout this talk, which C is not very strong and very good at. So C has functions, but I would not really call functions in C as first-class citizens. There are things you can do with functions in functional programming languages that you can't do in C. For example, usually functional programming languages, they allow you to simply write a variable to which you assign a function. You can't do this directly in C. You will always have to declare the function separately, and then you will have to assign the function in a separate step. Also, there are things like you can convert functions into other functions. We will see means of that in later parts of this talk. You also can't do that in C. So a lot of things you expect from functional programming languages are not there in C.
Just one more point. As I told you, right, this functional programming is a big fan of mathematics. So it has copied this higher order concept from the mathematics. So if you see higher order function, it's not a computer science term, it's a mathematics term. In computer science, we call it as a first class functions or a first class citizen. That is a computer science term.
One more point about your question. So you ask, if you have functions in C and you have function pointers in C and function pointers in C are higher order functions, why is C not a functional programming language? It is not a functional programming language, but you can do a lot of things in functional programming you can do in C. It's just like people usually assume in order to object-oriented programming, you need an object-oriented programming language. Not true. You can also do object-oriented programming in C. You can do it very fine. Yeah. Just if it gets polymorphic and you have more than one function, you have to code vtables in structures yourself. It can be a bit tedious, but you can do object-oriented programming in C. Yeah. So let's look at an example, and this is in C. It's qsort. It's an example even from the standard library. So I have a set of lines. I don't know how many they are. And this is how I sort my array of lines in C. I call the qsort function. But how does qsort know how to compare my data in order to sort it? Qsort is written in a very generic way. So I have to pass a function pointer to the function that actually compares my data so that qsort knows how to sort it. So that's what I do here. I have my function pointer, and here is my comparison function. So This shows that you can do higher order functions in C. You can also do it in Java. Same example, just in Java, how to sort stuff, how to apply higher order functions in Java. So in Java, we have these interfaces like comparator. And a lot of these interfaces just have one method. That's not really the key point, but having one method makes it simpler for some things. And so if you write a comparator for accounts, you've already seen the account class, and let's say you want to sort the accounts by their balance. So you would write the comparator maybe like this, and then you can sort your list like that. That is, so the sort method is a higher order function because it takes another function, the compare function, as an argument. Yeah, your question?
I just want to object you here that though the instance it is having one method, but still it is an object.
It is an object, but it doesn't. It also has no state.
In that here in a particular example we have not written, but still we can write, and it is an object. It can hold state.
Yes, but a higher order function does not necessarily have to be a pure function. I think it's strongly advised to be pure, but it does not have to be pure. These are two different concepts. Yes? Yes?
Something that will not hold its state alone, but it can change states. That is a function. My concept of that is function is something that can change the state, but it doesn't hold anything. If it holds the state, it is a local state. But here it is an object, so it can hold a state which is outside that thing. So particularly means it is upon the sort can be any call in Java that where we pass an object which has only one method.
Okay, so your objection is that actually we're passing an object, not a function, right? But the object is just a matter of the syntax in Java. And here you see the object, and with Java 8 you don't necessarily have to see the object. And this object is not holding state. Well, I wouldn't say this is the key point, because if you have a functional programming language and you really have syntax for higher order functions in a direct way, the function that you're passing could still be a function with side effects by changing some global variable. So I claim that you can pass an object and therefore you can change state is not the reason for saying it's not a higher order function. Now you can say, okay, you're passing an object, not a function, but what am I doing with the object? All that sort is doing with the object is calling the object's function that it's interested in. So syntactically, it is not a higher order function, but semantically, it is. Because the effect of this call is really just calling another function, calling the compare function. Nothing else happens. So the key point is also pointing out to you that although Java is not really a functional programming language, you can apply the concept of higher order functions.
Programming. So mainly the standard taken for the functional programming was that only if we need a function that we were only needing a function of compare, then why are creating an object of that? That was the main question raised by in Java that when we need a function, why we need any object to be created and passed to a sort method.
I'll rephrase the question. So the question was, why do we have to create an object in Java? Yeah, and that is why Java is not a functional programming language, and that's a deficit of Java. If you want to pass a function, because functions are not first-class citizens in Java, they always have to be accompanied by an object or a class holding them. That is what makes Java not a functional programming language. But if you apply this wrapping, you can still do functional programming.
In fact, that's what the Java 8 does, right? So we said in Java 8, they have the lambda expression. That means you can pass the function to other functions. So when you look at the code, you see that the function is getting passed to another function. But behind the scene, what Java compiler does is, it creates the object, wrap that function inside that object. So you don't see it, but that's what Java does it for you. Because in Java, there is no first-class support for the higher order function. And that's the point he wanted to make. But in Haskell, in contrary to this, in Haskell, you will pass the functions to other functions.
If we take a look at the object only has a method, it doesn't have any other state or something else, right? So sending this object is as good as sending a single function, like the one function.
Exactly. The point is sending the object is as good as. Your point?
Making the same thing. So they are.
We'll see the Java 8 example on the next slides. Yeah, we'll see it.
With the Java constraint. So yeah, that which you are saying that we are passing a function, but behind the rule, as said by Lina, that behind the rule the Java is doing that only, taking that function and putting it into object. At the end, it's playing with objects only. So it is not still playing with functions like functional programming.
Maybe it's because of the backward compatibility.
Yeah, but I think whether the engine is playing with objects or functions does not matter. It is purely a matter of how the engine physically organizes its data. Clojure, I think we can really call with good conscience a functional programming language. But when Clojure is running on the Java virtual machine, it is still dealing with objects to which the functions are bound. And I think it does not matter for the fact whether we call something functional programming or not. It's just whether you directly get the function pointer or whether you get it indirectly. It's a matter of the structure. So let's look at the improvements that Java 8 made. And it's exactly about what has been criticized, that if you look at Java before version 8, all I want is I actually want this part. This is what I'm interested in. Why do I have to write so much in order to pass a single function around in Java? Yeah? So that's one of the things that Java has improved. I think they can improve further, but Java 8 has already gone a big step compared to previous versions of Java. So let's look at how we would have done it in Java before 8. So this is if we would have written the comparator not separately, but if we would have integrated the comparator into the account class. This is how it looks like if you do it in Java 5. So you want to create a comparator that can compare by balance. So that is your variable, which, looking at the semantics, you want to be something like a reference to a function or a function pointer, if you want to call it that way. But you had to wrap it with a lot of syntax. You had to instantiate the interface explicitly. And then in that interface, you put the method. And then in the method, you put the code. So you have, it's like an onion. You want the core, but you have layers around it. And Java 8 helps you getting rid of these layers. So this is how it looks like with Lambda. So you can see how much is going away. The constructor call is going away. You no longer have the object wrapping it. Well, on the virtual machine you still have it, but the question is not whether there's an object on the virtual machine or not. The question is whether you, as a programmer, have to care about the object. Because even Clojure is going to use objects underneath. And you also no longer have to care about the method. You just say, okay, these are my parameters. And it has to evaluate to this. That's the block lambda. And if you're just returning one expression, you can do it even simpler. You can use an expression lambda, where you really just say, you map the parameters to this expression. And see how much Java 8 has inherited from functional programming languages. Usually in functional programming languages you also have type inference, where the type of something is so-called guessed by the compiler. It's of course not really a guess because it's a unique guess. If it wouldn't be the unique, the compiler would not accept your code. The compiler doesn't want it to be ambiguous. But you don't have to explicitly write the type. It's clear for the compiler that A1 and A2 are account objects. The compiler doesn't have to care about it. And then this is the expression to which it is mapped. And then, of course, you would not write it like this. I only wrote it like this for you so you can compare it nicely on the slides with the other two versions. So you see the evolution on the slide. You would actually, of course, write it like this. That makes it much shorter. And now see how close this gets to functional programming. This by balance is like a variable holding a function. And also see how well chosen the name is. For me, names are well chosen if when you read how the name is used, it reads very nicely. And saying accounts sort by balance, I think that reads very nicely. I'll show you another example. Okay, of course, almost no one is doing Swing these days. If you still have to do desktop, you would be using JavaFX, but most of us are probably on the web. Yeah, but I think most of us who know Java can relate to this example. Some time back you've learned these things. So we've been all using these action listeners to attach actions to our buttons in Java. And it was very, very tedious. It looked like this. And that is actually, it looks like hell if you do this a lot. And usually if you write a normal desktop application, it is full of this code. All you want to do is that when this button is used, that this code is executed. And you have from here to there and this all this additional stuff. And it looks awkward in the source code. It complicates the source code. It's a lot of weight, and it's always the same. It's so overly verbose. So Java 8 makes this a lot simpler now. In Java 8, you would write like this. You just say, okay, I get an event in my action listener, and then that's what I do with it. In this case, I just know I got the event, I can ignore it. The fact that I got the event already is my information. And usually in a program, you would, of course, have more than one action listener. Yeah, you have a question? Yep.
We can pass a lambda expression and a particular method, means actually you see that show message dialog. So E2, this method is there, whenever any input E is there, so this method is there. So Java will, the Java compiler will convert this to a listener class. So this scenario and a comparative scenario, this is one of these cases. Can we do any custom object, means custom classes there? Can we, I want to create from this E2 show message dialog, a listener object is created. In the previous slide, a comparator object was created. So can we, ABC, this is classes there, and I want the lambda expression that will get converted to this. Can we do this?
Okay, so the question is, can the examples that I showed was always an interface that's already defined in the Java API. Can we also do this with our own code where we are not using an interface from the API? Is that your question? Okay, the answer is yes, we can, but there's a limitation in Java. You always have, because it's a strongly typed and statically typed language, you always have to define an interface for it. If you're lucky, one of the interfaces defined in the API will suit your purpose. Like there's now an interface Java lang function. And it takes a parameter and gives you a return value. And if you're lucky, that is suited. If you're out of luck, you have to define your own interface, which defines the signature of the function. So in that case, Java is still more verbose than usually functional programming languages are. Does it answer your question? You?
Your custom interfaces, there is this functional annotation that has been added. You just need to stick to the contract that the interface will hold only just one value, and you mark it as functional.
No states.
No states.
You're allowed to have states. Yeah, well, the interface cannot hold states, but you can modify states inside that function. Nothing will prevent this. But I recommend using pure functions if possible. And you have to define an interface, and it has to have one method. And you can use the functional annotation on that interface, but this is primarily for documentation purposes. The compiler is not looking for it. For the compiler, every interface that has one method is a functional interface. But I recommend using the functional annotation to hint the programmers that it's meant to be used with lambda expressions. Okay, usually you would have more than one situation where you use this action listener. And for example, you might have an open menu item and a save menu item, and you want that for open, an open method is called, and you want that for save, a save method is called. And this is the pattern how you also can do it in Java 8. If you already have your methods, so you're not going for lambda expressions, but your methods that you want to call, and these methods match the signature that's expected by the interface, then you can simply refer to these methods. Now, if you're a Java programmer, the colon syntax looks maybe a bit awkward to you. Yeah, at least to me, it looks awkward. This is simply because in Java, methods and fields live in separate namespaces. In other words, you can give a field and a method in Java the same name. But now, how do you distinguish whether you're referring to a field or a method? If you want to call it, it's unique. If you have braces, you call it, so it's a method. If you don't have braces, you don't call it, so it's a field. But now with Java 8, with a method reference, you have a method, but you don't call it. So how do you distinguish this from a field? There could be a field named open. Maybe this would not be in the constructor, maybe this would be a field, because maybe I want to disable open. So, because fields and methods live in distinct namespaces, therefore there could be an ambiguous name. Java has to know when you're just referring to the method without calling that you're referring to a method, not to a field. They had to find something, and they just came up with colon. Yeah? Dot wouldn't have worked. So originally, when Java was created, it was thought that it's a good idea that you can have methods and fields with the same name. Now with Java 8, I think we have to think differently, and we have to live with these workarounds, because now you see Java is coming of age. Yeah, it's growing old. That's another example for higher order functions in Java. So this is a complete sort program. So you could call it on the command line just like the Unix program sort. It takes its standard input, reads all the lines, sorts them, and prints them on standard out in sorted sequence. It's not accepting arguments, so it's an incomplete program, but for the use case, sorting lines, reading from standard in, writing to standard out, it's complete, and it's working. So how does it work? And it works so short, you can write it in such a terse way nowadays, because Java 8 got stronger in functional programming. The key is line 10. In line 10, I take my input stream, or actually my buffered reader for reading the lines. I take a stream of strings by the function lines, I take the sorted representation, and then for each of them, I have it called print line. If you would have done it with Java 7 or earlier, you would have much more code. You would have to create a list. You would have to loop over the stream until readline returns null. And for each loop iteration, you would add an element to that list. Then you would sort that list. And then again, you would loop over that list and print the items. So you see that one of the benefits of functional programming can be that you can express the things in a very clear way, but also in a very terse way. And I think that significantly increases the maintainability of programs because the number of lines you have to deal with are much less. And the expressiveness of these lines is much more. And I think this is still, although it's very terse, it's easy to understand. In.lines, yeah, what else should it be as all the lines from in? Sorted. I think it's very clear what it is. For each, print it with a new line. There is no ambiguity, no misunderstanding. Yeah?
We mentioned that, first or second slide, we mentioned that whenever there is a IO thing or something, we are actually breaking the stuff. So here...
Very well noticed. Very well noticed.
Which probably is a side effect for that for each method, isn't it?
It's a side effect, very well noticed, and which means that this program is not a purely functional program. You have very well spotted it. So I'm here in this line 10, I'm benefiting from functional programming, but I'm not benefiting from not having side effects. I'm benefiting from higher order functions. I'm very happy that you spotted that actually I'm having side effects here by having I/O. Because it shows that these concepts of functional programming, they can also be used independently of each other. I'm having a higher order function. For each is a higher order function because it takes another function as an argument, but the function that I'm taking as an argument is not a pure function, as you've already learned and spotted very well. If I would want it to be more functional, what would I actually have to do? I would first have to collect the strings by not making I/O here, but by concatenating the strings until I have all my output, and then at the end I would print it. Instead of printing it inside the loop, I would print it at the very last final step outside the loop. And then, because here, as you can see, we are calling that function, which means that print line is in the deep part of the call tree. And we would not want side effects in the deep part of the call tree if we really go for pure functions. We only want that side effects are in the upper part, in the layer around it. You could say it in the shell around the core. Yeah, well spotted. Yeah? Can you speak a little bit louder?
I'm asking how getting function know about in variables that we are passing in for distributor.
You're asking about in.
In variable that we pass in the parameter.
Yeah.
Distributor.
I think it's moving to line number 6.
Line number 6. This is coming from the static import in line 2. I have a static import here in line 2 where I import all the static fields and methods from system. And in is one of the fields in the class system. So this in here, it takes Java lang system.in. Does this answer your question? Okay. Okay. The question is, in line 10, out colon print line has a side effect. how does the compiler know that it must not run it in parallel? Because if it has a side effect, run it in parallel would be bad. Is that your question? So the answer is, in Java, you have two types of streams. You have streams and parallel streams. And streams, if they're not parallel streams, they are sequential. They have some benefits of the streams of functional programming, which means they can be lazy, for example. We'll talk about that later. But they are not in parallel. So it is guaranteed that, this is a normal sequential stream, this still is a normal sequential stream, and this again is a normal sequential operation. So here I'm not benefiting from the purity of functions. So this is an extension basically of your question. I'm not benefiting of the purity of functions for parallelism because I'm having a side effect. But also, if I'm having something sorted, there are limitations on the parallelism. The parallelism, if I'm processing sorted data and I want to keep the sorting intact, the parallelism cannot be random. The parallelism has to follow the sequence of the sorting. But it could still be done in parallel. You could still take the first half and the second half and concatenate them separately. Yeah, that could be done in parallel. And it's possible in Java. Which means that if I would have followed the purity, I could actually, at this point, have created a parallel sequential stream and would have benefited of a multi-core CPU, at least for the string concatenation.
Here, as a programmer, I am saying whether this code could be run parallel or not. It's not the compiler that will
Exactly.
determine what kind of stream I use.
Well,
The compiler figures out. Otherwise, as a programmer, I have to make sure like this code can be run in parallel or whether it cannot.
Yeah.
Be run.
The Java programming language does not support automatic parallelism as the compiler or language feature. Parallelism is explicit, always. And I have two ways. Either I create the threads myself, or I have something in the API as a service which creates the threads for me, like parallel stream. But there will always be something which is an explicit call on something, either a thread constructor or something else, which will make things parallel in Java. There's no implicit parallelism. It always is somewhere explicit. There might be some APIs or engines or frameworks for web, for example. You want that your HTTP requests are processed in parallel, of course, not sequentially. But again, the new thread call is there in the framework. It's not in the compiler. You also want to say them?
So it is explicit. The programmer has to do it. But it is much easier in case of functional programming. Because whatever program you are doing, you will try to write it in declarative ways, one of the things. And second thing is, if you try to write it pure functions, everything, then it will be easier for you to parallelize.
Yeah.
So there are much more constructs given by functional programming than normal imperative programming.
Let's assume I would use string concatenation here. I would use a collector that finally gives me a string by concatenating two elements. Then all I would have to do in order to make it parallel would be to insert a call parallel stream here. That is very simple. If I would not have this feature, if I would use the traditional way of parallelism in Java, I would have to create my own thread. And the simplest way would probably be to use one of the pools provided by executor service. But I would still have to create my own runnable instance with my run method. I can, of course, then use Java 8 to make it simpler, but I still have to tell the executor service, create threads. And if I'm using the executor service, I will actually have a problem to solve. The problem is, how do the threads get their input data, and how do the threads create the output data? And I will have to think a lot about synchronization in that case. If I have multiple threads operating on the output data, how do I make it synchronized? If I'm using these streams and I use whatever the stream API provides as facilities, all I have to do is parallel stream here and a collector that takes two elements and combines them. All the parallelism problems are solved. I don't need to take care of synchronization. I don't need to create threads myself. Everything is done in background by the API. Because functional programming makes this easier. But as already very well spotted by this person in the audience, this cannot be run in parallel because I'm not using pure functions. Bad me. Very well spotted.
Throwing an exception makes a function
Um, I think this is better as answered by Lena.
Right. Again, that's a very debatable. Why it is seen as a side effect? Because if you're throwing an exception from a function, then output really depends on if your caller is catching the exception, and it might be doing something else. And if caller is not catching and just throwing it back, you'll get the different output. So it really depends on caller if it is catching it or not catching it. So in a way, that causes the side effect.
Yeah, basically, what we learned with pure functions is that whenever you call it, you get the same result. But when you have exceptions in the in higher order functions, you can no longer reason about the purity of the caller function of that higher order function if the called function may throw an exception. So it's disputable whether exceptions really are a side effect in the very strict meaning of side effect. But definitely exceptions are a problem for the purity of higher order functions. They are definitely problematic. I think if we look at this example, it's not, yeah? Yeah.
There is one more way to think whether there is a side effect or not is any function that is context independent will actually tell you whether it is having any side effect, any dependency on the system or not. So if you are throwing an exception and higher in the layers, if there is someone who is catching that exception, the program is different. So looking at that, whatever function I'm looking at, if it is throwing an exception, I don't know whether this will terminate my application or not, because there might be someone who is catching that exception. So I cannot locally reason about that. I cannot locally say that this will happen in my system. I have to actually go up in the system, in the call hierarchy, and see whether someone is handling that or not.
Yeah, I'll repeat it for the recording. So his point was, if you have exceptions, you cannot locally reason about the flow of control. And of course, you might then counter-argue, but what about parameters and returns? But you can still reason very nicely about them because it's only one level, the caller or the callee, that you have to go in order to reason about what happens. But if you have exceptions, the purpose of exceptions is to actually jump a whole bunch of callers in the call tree. And it means it breaks local reasoning. That's also something what the pure functions are about. They're about local reasoning. Yeah? And the referential transparency is also not true if you deal with exceptions. Yeah. I think one of the things we're going to learn in the future is how bad are exceptions. We know it breaks it, and something that we as a community now have to gain experience with is how bad are exceptions. I think if you compare C and C++ or C and Java, we cannot say that exceptions are bad. I think if it comes to error handling, exceptions have served us very, very well. But the same thing we can say for object-oriented programming in a way where we modify state. It has served us very, very well until we encounter race conditions and parallelism. Yeah? Then it breaks. And we also learned that sometimes in the 90s or early 2000s, we probably were overdoing object-oriented programming. But you can't tell how much object-oriented programming is overdoing it unless you try to overdo it, either intentionally or accidentally. And I think the same is going to be true for functional programming. we know lots about these mathematical concepts, and one of these things, the mathematical concept, is telling us exceptions violate purity. That is certainly true, that statement. But what is our duty as community now is finding out how bad is it. We do not yet know. We have experiences where we definitely see that exceptions in functional programming break it, and they make it bad. And on the other hand, our experience from object-oriented programming tells us exceptions are good. And we'll have to find out what is the truth in the future. And it could be that we find out that we have to be pragmatic. Exceptions break purity, but we can accept it somehow. Or it could be we find out exceptions break purity, and that is really bad. And therefore, we have to come up with different concepts in exception handling and maybe go back to return values, or what's not going to be in this talk, but what's going to be in next talk, like other concepts, like monads and other things in functional programming, which maybe deal with these things in better ways. Yeah? And you will hear different voices, different opinions on this topic, and we need to gain more experience as a community until we know the answer. I think regarding functional programming, now that it's no longer in its academic niche, but it's coming out in the field, we are in a similar situation as with object-oriented programming we were in the 90s, in the early 90s. It left the academic niche, it became in widespread use, and we had to gain experience in the community about what things are good about it, what things are not so good about it. Similar situation I think we are in right now with functional programming. So we'll have to learn. And I think there's no right or wrong regarding are exceptions now really bad or not. The facts are there. Exceptions violate purity. But whether this is having a bad effect always or just sometimes, we will have to learn with experience and then draw the conclusions. But what you can see is, back to the code, line 10, you can already benefit from functional programming without going the whole way. This is also one of the things I wanted to show you to you. You don't have to take the big step saying, I have to be pure and I have to use higher order functions and all the other things that are going to come on the slides in order to benefit from functional. You can already take one thing. You can take pure functions and it makes your code more easier to reason about. It doesn't mean that you have to turn all of your functions into pure functions immediately. It already helps identifying one after another and going step by step. And you can also benefit from higher order functions because you've already benefited from it. Yeah, you've already been using it. As I told you, you just had wrappers around it, like function pointers in C, all objects wrapping one method interfaces in Java. And to show you the modeling side of it and why keep object-oriented programming aside. We still have the problem we model big systems. Even if you do purely functional programming in Haskell, let's say, you still model a big system, and if you model a big system, you're confronted with architectural questions. You're confronted with questions of coupling and cohesion. You're confronted with a question, what, for example, if you want to reuse component A without component B? What if, in that situation, component A depends on component B? You couldn't reuse it. So in order to reuse it, what you want to do is you want to invert that dependency. There's the D in the solid principles. And let's take an example. You want to sort articles, online shop. Usual example. So if you write your sort algorithm in a way that it knows about articles, then you've coupled the sort logic to the article logic. You can't reuse sort. So what you have to do is you have to decouple it in a way that the dependency is inverted. So what you do is you introduce something where the compile time dependency shows in the other direction. Now at compile time, component B, the article, depends on the sorting, not the other way around. The sorting depends on a higher level abstract thing, and something abstract, which is part of itself. You've inverted that dependency. So that's the dependency inversion principle. It's one of the solid principles which are important for software architecture to decouple the components. And now component A, the sort, can be reused. And that's a problem that you have in object-oriented programs just as well as you have it in functional programs. And higher order functions are just another way of polymorphism. Because the behavior depends on what function pointer you pass in. That's also a reason why I'm not worried about whether the mechanics, the underlying mechanics, are actually really dealing with a function pointer or an object pointer. In a different talk, not today, but in a different talk, I'll actually raise the question whether functions and objects are different at all. I think we are doing a big mistake in languages like Java or C++ or C, where we treat functions and objects in a very, very different way from the syntax perspective. I actually came to think about this when I did behavior-driven development. Then I had my given, when, then scheme, and I tried to nest it nicely to reuse my givens. And then, is my given a class or is it a method? I suddenly faced this question, and I wondered, but that's something for a different talk. So, higher order functions are a form of polymorphism. They serve the dependency inversion principle to decouple your parts. So now you know how to do a step of architecture in functional programming, and they decouple software entities and make it reusable. So that's now also the answer to the question, why do you use higher order functions? If you look at it in object-oriented terms, higher order functions can always be expressed using objects. And that's what Java and Clojure, by the way, also do on the virtual machine. On the low level, they express it using objects because that's how the virtual machine thinks. The virtual machine thinks in nouns. And all verbs that you're using on the virtual machine have to be accompanied by nouns. It's the kingdom of nouns. Java is the kingdom of nouns. Yeah? Functional programming is the kingdom of verbs. And if you want to bring it on the virtual machine, you have to follow the rules of the virtual machine. Every verb has to be accompanied by a noun. Every function has to be accompanied by an enclosing object or class. Not every expression using object is also a higher order function. Yeah, that's also to say, if you want to really speak of higher order functions in a more strict way, you really at least want to think into the direction of purity. You may be not always doing it for reasons of pragmatism or also for reasons of learning. We want to learn step by step. And we will always face questions like, how do I do this functional? And we'll not always have the answers right away. So I personally recommend if you have side effects, you may call it method. And if you don't have a side effect, call it function. Okay, these are the references. Yeah, and I think now we'll have a short break of about 5 minutes.
Okay, so next thing what we're going to see is the imperative and the declarative, right? Again, these are the paradigms, the programming paradigms, imperative and declarative. So without going into the theoretical definitions of it, we are going to understand this with example. So this is a simple Java program written in an imperative style. What it is doing is, it is finding, given a list, it is finding an even number, doubling those even number, and then finally sum it up and returning the total. So that's the program about that. Okay? Here's some other program. Can you guess what it is doing? By the way, okay, I'll come to that one. By the way, this is written in Scala. If you don't understand the Scala, don't worry about it. Think it as a pseudocode. And see the response I got, right? When I asked what this program is doing,
within a second's time, people say, okay, it is doing the same thing. And that's the beauty of the declarative style. Imagine in previous slide, if I have not shown you this description, what it is doing, then you have to really scratch your head in order to understand what it is doing. Though this language, that's a Java language, right? That's a native language where you code day and night. That's your mainstream language, right? Still you need to scratch your head. Scratch your head. This language is alien to some of you, but still you are able to predict what it is doing. So if you see what we are doing in this program, right? We are finding the even numbers. So that's this bit, a small piece which is doing this job, doubling it up and summing it up, right? So the things which are actually needs to be done are done in very small piece of code, right? But then also we have written so much of boilerplate code around it. Why do you think? Why we have written that?
That's how Java works.
Exactly.
Until Java 7.
Yeah. So I'll make more generalized statement that why we have written so much of boilerplate code around it, because instead of focusing on what needs to be done, because this what needs to be done is in highlighted small lines, we have also said how it needs to be done. For example, if you want to find the even number, what we are saying, take a list, iterate over it one by one, take one element and then find if it is even or not, right? So we, along with what to do, we are also specified how it needs to be done, and that has made it ugly, and that's why it has made it complicated. In contrary to that, in this example, we have just focused on what to do with, right? We said, let's not filter, right? That means do some kind of filtering based on that condition. Next we say map. Map means I can relate map from one value to another. We are saying double it up, and finally we are saying it sum it up. So we just focus on what needs to be done, and then the how part is completely left on the language, and that's why it has become so crisp and beautiful. And that's the declarative style of programming, where you just focus on what needs to be done, and the how part is left on the language. In previous slide, we, along with what, we have also said how it needs to be done. If I have to explain you this concept with some real world analogy, then I can say, okay, imagine that it's Sunday today and I feel like eating a pizza. Since I'm a vegetarian, I would like to have the veg pizza, right? I like the extra cheese and I like my pizza to be crispy, right? So I have the three requirements. I like the veg pizza, I like some extra cheese, and I want my pizza to be crispy. If I have, so this is my requirement and I want my pizza. So I have two options to get the pizza. One is the imperative style of approach. In that, what I'll do is I'll prepare the pizza on my own. That means everything I have to do on my own. That means if I need vegetables, if vegetables are not there already in my fridge, I need to get them, get it home, chop it up, spread it on the pizza base, bake it, grate the cheese, make it crisp, and then eat it, right? You imagine the long procedure, because everything I am doing on my own. The other option I have is, I know what are my requirements. I'll just call up a restaurant and I'll say, okay, I want the pizza. Can you give me the veg pizza? Can you put some extra cheese on it? And can you make it crisp? That's the declarative style of it. To restaurant, I told my requirements. How they prepare it is their head, right? So, do you understand the difference between the declarative and the imperative style? We can take one more example from the, yeah.
So, in declarative style, it's indirectly we are doing separation of duties, you can say.
We are eliminating the how part, not the separation of duty. We are eliminating the how part, right? I am saying, I want the even numbers, right? How do you do it? You iterate over it, or do you do whatever with it? I don't know. I just want the even numbers. So we are eliminating that how part, and that's the declarative style.
I think we will demand this.
Sorry?
I think we will demand demand is I am demanding even number and I am dividing it to bigger double number.
Yeah, whatever you want to call. You want to call it as a demand, whatever you want to call it as a requirement, but we are just saying what I want. Right? Or if I am modest, I will say request. I will not say demand. So it just Alright, so if we have to take one more example in order to understand those declarative and the imperative concepts. So how many of you have used the AND? It's a build tool, right? So do you know the difference between AND and Maven? If in AND you want war as an artifact, right? Then in order to get that war, you need to write all that task. How do you package the war? That's the imperative style. Whereas in Maven, you just say, okay, I want the war file, or you want the executable jar file, and how it needs to be packaged is left on that tool, Maven. So that's a declarative style. So your all object-oriented languages falls in imperative paradigm, right? And since you know object-oriented is your mainstream languages, so you know these are the few characteristics of an imperative paradigm. The first, we have already seen that how to do it, right? It just focuses on how to do it and makes your code ugly. Next thing is very important, the mutability, right? So here if you see that total variable is a mutable variable. Why is it mutable? Because inside that for loop, each time we are changing its value. That's why that's a mutable variable. Do you remember our earlier one of the slide where we have the global balance state, global mutable balance state, and we said that it's bad because that is introducing the impurity or the side effect in my code. So forget about the functional programming, forget about you don't know about the side effects, you don't know about the purity, right? If you're coding in Java, then also having the shared global mutable state is a bad thing. Why do you think that's a bad thing? Having a shared global mutable state, why is it a bad thing?
Because you cannot guarantee the
Right? Because in the concurrent environment, it will give you the undesired results if you have the global mutable state. So, if you look at this mutability, this is not the global, right? This is a local mutability. It is not as bad as that global mutability. But still it is a bad because it lets you write the code in an imperative style. And that's why local mutability is also bad. So in general, mutability is bad, whether it's a local mutability or global mutability. It is bad and you should avoid it as much as possible. So one of my friends tweeted some days back, what he mentioned was, I'm not smart enough to introduce the mutability in my code. Because he knows that if he introduces the...
You don't take care of the audio, please.
Yeah. So if he introduces the mutability in his code, then he knows that we have to pay a cost. And that's why the mutability is the bad thing and you should avoid it as much as possible. Since I assume that you all code in object-oriented programming, so I'm not going to go into the details of it. These are the few characteristics of object-oriented programming, that you deal with the null values, you have the side effects, you have the locking and the synchronization because you have the shared global mutable state. And all object-oriented programming falls into the imperative paradigm. Declarative paradigm, all functional...
Yeah, so one quick question regarding that. So whenever we are calling a map method or something, that should be implemented in language construct, right? So somebody like Scala or someone. So are they actually not iterating and calling recursive function?
They are doing the same thing. That's what I'm saying. It's actually doing the same thing, but they are doing on behalf of you. They are taking care. They are taking care of that.
Do you care?
Yeah.
I don't. But if they are calling iteration, then there would be a shared state already, a local shared state, right? So I thought,
yeah. So if we go back, let's first look at this from a different perspective. How many chances do you have to get this wrong?
many times.
You have lots of chances to get this wrong, isn't it? Yes. And we've already reduced the chances by being smart and using the for each loops in Java. We've already reduced it. Yeah? But you still have a lot of chances of getting this wrong. How many chances are there to get that wrong? There are not many chances. And if you get this wrong, you really get it wrong in the core parts, where you wouldn't have got it wrong anyway. If you get what wrong, yeah, it means you really have a requirements error. But you can hardly do an implementation error here. Whereas here, you have lots of chances of doing an implementation error. Of course, in some way, this code is doing the same thing as this code. They're doing the same things. So it's not really about what is going on the CPU, where we want the job done. The question is, how can we phrase the source code in order to get that job done? And I think it's very obvious that this functional style, for this example, the phrasing of it is much more maintainable. There are much less places where we can do errors. It's very difficult to get this part of code wrong. And that is about many aspects that we could get wrong. And one of these aspects is about dealing with the state. So for example, you write, in the simplest way, it probably, if it's not parallel, it probably has a loop. And if it has a loop, it probably has a mutating state. But I don't need to take care of that. It's the implementation that is taking care of that. And basically, what functional programming has done for us in this situation is it has made things like for loops and for loops with nested ifs reusable. Yeah? This map and this filter, they are reusable loops in some sense.
Okay,
Yeah?
so how can have multiple implementation in the language construct? Like one is a recursion, one is a loop, the third one is more of.
I don't know about Scala. I simply answer this for Java. In Java, you have stream and you have parallel stream. Yeah? And one is doing it in one way and the other is doing it in a different way. So I don't need to take care of. Your question?
Parallel connections. You have parallel connections in Scala. Basically, if you are using these higher order functions, the implementation is left to the language, right? Exactly. So they can do better optimization on your behalf rather than you are doing those things, right? So that is also one advantage if you are using these language constructs.
Yeah. To support your point, now let's assume this isn't 5 numbers. Let's assume this is 5,000 or 5 million numbers, a high number. Then we would probably be interested in getting this summed up as quickly as possible. If we specify how it is summed up, we have to change this code a lot in order to get the sum being done in parallel. What do you have to do to get the sum being calculated in parallel in Scala?
Yeah, all you need to do is put par in there. List.par.
Here, you will just put a par word, and that's it. It will compute this
It
parallel.
will convert that list into a parallel collection, which is able to carry out all the tasks in parallel. And there is a whole lot of logic in dividing the task and all this.
Yeah.
Actually, this to answer your question, these functions you can go ahead and you can write in your code, that filter, map, and sum, whatever. But this function are already written in Scala, and they are written in such a way that they have used the immutability. How we can use the immutable feature, the recursion, the tail recursion part is one of the features of Scala. So they have made use of that, and they have already provided. They have written this function in there, so you can directly go and use it.
Right, and in Java, right? So there is no inbuilt support before Java 8. inbuilt support for such declarative programming, right? So there are libraries which you can use, for example, Java, which allows you to write code in a declarative style, where you already have those functions, filter, map, and which you can use it. Okay. So we were looking at the declarative paradigm, right? So as you know by now, that it just focuses on the what part and the how part is left on the language. Immutability, we've already seen that the mutability is bad. So in functional programming, we write the code with the immutability. That means we do not write the for loops, right? Because in the for loops, you know how many times you have done that, I equals to 0, I plus plus. So we replace that for loops with the recursion, and that's what we write in a functional programming or in a declarative paradigm. So that's about the declarative paradigm.
Okay, so I now talk about persistent data structures. So we've already talked about immutability several times. This will be another occasion to talk about immutability in a very significant way. I quickly go back to this example because it is really showing certain aspects of that topic very nicely. If you want to do this in parallel, the difficulty is the mutability of total. That is actually the difficulty of the parallelization. That you have one shared state, variable total, in which you create the sum. That is the difficulty. And as we already learned in the beginning, we want pure functions, functions which have no side effects. But if you want to do things in parallel, you actually have to make sure that more than one CPU core can really do it in parallel. So you actually need separate code. And the level on which we separate code is on the level of functions somehow. So there's again a strength of functional programming languages that you do not have to create huge constructs like threads where you specify how parallelization is done. You just say what has to be parallelized. And that is very simple, very terse. Now let's go to first of all, if you know Git, yeah. So for this part, you just get popcorn, lean back, enjoy. If you know Git internals, you basically already know persistent data structures. You maybe didn't know that it's called persistent data structures. But, yeah, it's just a name. If you don't know Git internals, listen carefully, because whatever you learn now is also telling you how Git works internally. A persistent data structure is a data structure you can imagine as a Java program as if all fields in the data structure are final. And the previous version, therefore, of something is always preserved if you change it. Because you can't change it, you have to create a new instance of it, which has the modified data. And that means you deal with copies. Now, sometimes when you tell this to people for the first time, you have to deal with copies, people start getting worried. About what are people starting to get worried if they hear copy?
The memory?
Yes, they start getting worried about memory. But if you're an experienced object-oriented programmer, you already have started using persistent data structures. Maybe you didn't know it under the term persistent data structures. Maybe you simply called it immutable objects. And you started using that in order to preserve memory. Now let's look at an example. There's a point object. You can also imagine this is a date object. Yeah? Date is kind of a hot topic in Java. Yeah. I don't know for how many times they already updated the date and time API, and I don't know for how many times they're still going to do it again. I got so sick of and tired of the topic, I didn't look into the latest version yet, I admit. I just was too scared. And the point about why I was too scared is, I thought, did they get it right this time? And what I was worried about is, did they finally make the core data class immutable? Yeah. that was what was my biggest worry. Why was I worrying about that? I actually started worrying about that when functional programming was far, far away from me, when it was not at all in my head. The first time I actually did functional programming was in 1985. I learned the Logo programming language. I don't know if some of you have heard it. You have a turtle, which is a kind of a graphical cursor, and you can tell it up 20 and right 20 and down 20 and left 20, and then you have a square. And then you can create this square function, and then you can say square 10, square 20, square 30, actually two-dimensional coordinates, imagine 10, 0, 20, 0, 30, 0. And then you have 3 squares. And the functional programming language was made for kids. I was a kid. I didn't understand it, but years later it helped me, this memory of Logo helped me understanding functional programming. I didn't understand it back then, but whatever traces it had left in my brain, it helped me later. But when I was thinking about this, it was not at all in my head. I didn't think of functional programming. What I was thinking about was, I simply had a bug in a program. It was a calendar application. And in a calendar application, what you have? You have events. And these events are on dates. And there was a part of the program that was where you could clone an event. And you created a new event, and let's save memory. We would just clone the object, we don't clone the date. And we thought it makes sense. So the two events point to the same date object. But what did the code do that actually changed the date of the event? It modified the date object, which meant that the copied event would always be at the same date as the original event, and the other way around. When you change the date of one, you also change the date of the other. Which means that these mutable objects, they endanger the referential integrity of object-oriented software. And that's again a point where functional programming and the newer experiences of object-oriented programming meet and embrace each other. We're actually approaching the topic of immutability not just from one side. We're not only approaching it from our academic, now going into the field perspective of functional programming. We've already had our OOP experiences where we said, if we could go back to Java 1, we would make dimension immutable, we would make point immutable, and would make date immutable. What is the solution in Java? If, for example, you're on the GUI, you're a GUI component, and you have already mutable classes like dimension or point, and these are return values of your getters. In order to protect you from change, you do not return the original value, you return a copy. This mechanism is called defensive cloning. And every time I ask a button, give me a position, like get location, and then I get the point object with x and y, I've actually got a copy. I always get a copy. When I call get, I get a copy. It allocates memory. Actually, we should think of memory allocation not strictly as a side effect, but we should a bit consider it. And what would be probably more often in software, getter or setter? Probably the getter. What would make more sense, to allocate memory when setting or to allocate memory when getting? I think it makes more sense to allocate the memory when setting. And that's where the idea also comes from. And this would be a point class that is immutable. So whenever you create a new point and a new position, you really have to create a new object. It also makes sense from the perspective of semantics. If you think of a point 2, 2, and a point 2, 3, they simply are different points. It cannot be the same point. The values x and y for a point make up the object's identity. When you would change them, you would change the identity of the object. Same for the date. So it also makes sense from a semantic perspective. Now let's look at a real persistent data structure. I'm showing you from the implementation perspective. How would you implement a list as a persistent data structure for a language like Java that doesn't have it already? In Java, it's a list where the nodes simply only have final fields. Your final field next, pointing to the next node, and the final field data, pointing to the data of this list element. And when you create a list with one element, you just create like this. Two with more elements, just change them. Yeah? Linked list. And this means that in some situations you have to copy things into a new list, and in other situations you can reuse the existing list. And I show you by showing you two lists and how they are concatenated when they are persistent data structures. That's what is going on under the hood if you're working with these languages like Scala, Haskell, Prolog. It's what's going on with lists under the hood. So if I concatenate the two lists, I can reuse the list. That is the tail part. I don't need to change anything, but the head part, I need to create new nodes and items. And we're not worried about that as functional programmers, because usually it turns out that in most algorithms, this part is the smaller part and this part is the bigger part. Because usually when you deal with lists, you usually deal with the head and the tail. The head would be one element, and the tail would be all the others. That's the example for the list, and that's the code for a tree. So you have the same thing, just that instead of having the next node, you have a left and a right node. But it also works for trees. And the same thing as if you have a list and you insert an item, or you concatenate lists, you can reuse parts and other parts have to be copied. The same would be true for the tree. Yeah?
Can you go back to the previous slides? Just for the food for thought, can we actually use A and B as well? Because C is just, just the C part is changing.
That's a very good question. Thanks for asking it. I actually have to recreate the entire list, because when I have to redo C, because why do I have to redo C? Because next was final. So I have to redo C in order to change the previously null value to point to D. But it means I have a new C, which means I have to update the next part of B as well. That's why all the head of the list is changing. Very good question, thanks.
It's a ripple effect, basically.
Yes. From an academic perspective, we actually also have 3 levels of persistence in functional programming languages. We have partially persistent. In partially persistent, you can query all versions, but you can update only the latest version of an object. It means that an object is by itself immutable, but as soon as you refer to it from a copy, it becomes immutable. We have fully persistent. That's actually then truly functional. You can query all versions and update all versions. And what languages like Haskell actually really use is fluently persistent, which means that you have combinators, like the list concatenation, and it leads to a directed acyclic graph between the objects. And that's same thing as data is stored internally in Git, and a direct acyclic graph, by the way, is also the structure of a software system with a perfect architecture. It should also be a directed acyclic graph. Okay, so that's persistent data structures. So now you know how in data structures in functional programming language we deal with the fact how to make it immutable, how to avoid side effects, how to establish the purity. Anything you want to add about this?
Okay, now the lazy evaluation. Again, a very, very important feature from functional programming. Please laugh. I created this slide. Okay, now let's get into some serious business. So these are two evaluation strategies. One is the strict evaluation and another is the non-strict evaluation. And as the trend goes, we are not going to go into the theoretical definition of it, and we are going to understand this by example. So what will be the output of this program? 15, simple, right? What will be the output of this program? नहीं, सिर्फ नीचे वाला. It's not that difficult. Right? So, okay. Let me go line by line. You're calling the... Oh, they showed you the output. But what you're doing is you're calling the product method and then it's printing the product method, and now it is returning the result and printing the result, right? So that's the expected and this simple. That's the strict evaluation. What is strict evaluation is whenever you're trying to assign something, whenever you're trying to assign some expression to a variable, that expression is immediately getting evaluated. That's the strict evaluation. Whenever you're calling a function, that function parameter is immediately getting assigned to a function parameter. That's the strict evaluation. Okay, since you assume that you code in object-oriented language or a Java, so this behavior is actually familiar to you. You didn't notice that this is what is happening because it is so implicit for you. But that's the strict evaluation. So if I have to define it, I would say whenever an expression is getting assigned to a variable, it is getting immediately evaluated. And same thing happens when you call the function. That function parameter is evaluated and it's assigned to a function parameter. Java uses this strict evaluation. You already know this, but I think you were not aware that it is called as the strict evaluation. So we've already seen what does that mean. Evaluate immediately at the time of assignment. You know, in Java or in any object-oriented programming, there are two ways you can pass the function parameter. One is the call by value and another is the call by reference. I'm not going to go into the details of it because you already know it. What are we interested mainly is in non-strict evaluation. So all our object-oriented languages uses the strict evaluation. Now since you know what is the strict evaluation, can you guess what will be the output of this function called multiply?
Exception.
Exactly. Divide by zero error, right? According to the strict evaluation law, whenever we are calling this function, this parameter is tries to evaluate it before it assigns to this variable, and it throws an divide by zero error. So if you look at this particular example, right, it seems like a problem because in this example, what we are doing is we are passing the true here, right? So it should actually go here if true and return 100. That I is not even particular scenario, but still this function is failing, and that's what the problem is. That's what the problem with the strict evaluation. Now we will see what is the non-strict evaluation. So what is the strict evaluation first? What is the strict evaluation? Evaluation happens during the time of assignment. We all know that, right? What is the non-strict evaluation? Non-strict evaluation means evaluation happens only when it is needed or only when that variable is being used. It doesn't happen during the time of assignment. So you know, we've already seen there are two types of assignment. One is the function parameter assignment and the second is the variable assignment. Now, if we know what is the non-strict assignment, that the non-strict assignment means evaluation will happen only when it is needed. So, if you know what is the non-strict evaluation, and this is the function call, right, what will be the output of this program? 100, right? Because when you call the product, it won't assign true to this flag or 10 by 0 to none, because they are not yet used. It will come to next line, it will say if flag. Oh, that means now I am being used and now it's a time to evaluate me. Let me evaluate. What is flag? Flag is true, right? And it say, oh, if it is true, I'm going to return 100. So it's not going to evaluate num. And that's why in this scenario, we don't get the divide by 0. And that's the non-strict evaluation. So functional programming supports this kind of evaluation, a non-strict evaluation. That means things are evaluated only when it is needed. It won't evaluate it unnecessary like the strict evaluation. So the output of this program, as you already answered, is 100. Right? So we said there are two types of assignment. One is the function parameter assignment. Right? We've already seen that. That's called as the call by name. When the function parameter assignment happens non-strictly, we've just seen that, right? That thing is called as call by name. When the variable assignment happens non-strictly, then that's called as a call by name or the lazy evaluation. We're going to see the example, but this is what the difference between the call by name and the call by name. When the function parameter assignments happens non-strictly, then that is called as the call by name. And when the non-strict assignment happens for a variable, it is called as the lazy evaluation. Most of the times, this lazy evaluation and the non-strict evaluation are used interchangeably, but they are different. Okay, so now we are going to see what is lazy evaluation. So, before going into the example of a lazy evaluation, I assume that you all know what singleton class is, right? So, this is my singleton class, and if I call singleton.getInstance, what will happen? It will say, okay, instance. Instance is not created because until now it was not needed. And what will it will do? It will create a new instance and it will need it. What kind of behavior is this? Non-strict, right? Because until now it was not needed, that instance thing. And when it needed, it created and returned to you. Next time when you call the singleton.getInstance, what will happen? Right? That the instance is already created, it will return you that instant. And that's the lazy evaluation. So lazy evaluation is first is it's a non-strict evaluation. That means it will evaluate only when it is needed. And second, it will evaluate only once. Right? That's the non-strict evaluation. That's the lazy evaluation. You're already done this thing in Java, but you were not aware that these things are called as the lazy evaluation. In functional programming, we get the by default support for lazy evaluation. In Java, we don't get that. That's why we have to write this bookkeeping code to, to showcase a lazy style. That's the lazy evaluation. The another example could be a caching. Many times we implement the caching in our code, right, for the performance reason. So what it does is, whenever we want something, we first try to look up from the cache. If it is not there, we get it from database or whatever, and then we store it in the cache. Next time when we need it, we get it from the cache. That's the lazy evaluation, right? Evaluate it or get it only when needed and evaluate it only once. So that's about the lazy evaluation. So now I understand that, now I think that you understand what is a lazy evaluation. Again, I'll repeat, it will evaluate only when it is needed, and second, it will evaluate only once. So if you know now what is the lazy evaluation, let's try to understand what will be the output of this piece of code. So now the function of call, I said it's a lazy, that means do not go into that function immediately, right? That's a non-strict behavior. So it won't go into this function. Instead, it will come to this line and it will print 333, right? Then it will come to the println result, and then it says, oh, now the result being used, and now it's time to evaluate me. That means now it will go to the function, it will go inside this and it will print inside function, right? And finally, it will print the result because we are asking it to print it, and that's why it printed. Next time when I call the result, what will be the output? Hello world, exactly, right? Because in lazy evaluation, we said things are evaluated only once, right? So result, it says, oh, I'm already being evaluated. I'm already being evaluated, non-strictly. Next time, whenever I need it, I'm gonna lazily use that value. So functional programming uses this lazy evaluation, and it has got the by default support for the lazy evaluation. If you have to provide such mechanism in your Java program, then you need to write this bookkeeping logic. Oh, if it is already created, then if else, return it once, or that logic you have to write it on your own. But in functional programming, we get the out-of-box support for such things. That is the lazy evaluation.
Quick question.
Yeah.
Previous slide. What if I don't mark the result variable as lazy?
Where?
Like,
Here.
Next slide. Yeah.
Yeah.
I remove the lazy keyword.
Yeah.
And then what happens?
Yeah, that happens. Then that happens. What happens in Java?
Inside.
Sorry. So that's a very good question. Why? Because that was a very good spot. Because, by the way, that's a Scala code, right?
Right.
So reason why you have to give that lazy thing, as I answered, Scala is a multi-paradigm language. It's an object-oriented language, it's a functional programming language also. So it has to support both the strict evaluation and the non-strict evaluation. And that's why it has provided that construct. Okay, if you say lazy, that means I know I have to evaluate it non-strictly. But the languages like Haskell, right, which I told you millions of times, that it's a purely functional language, right, where the by default evaluation strategy is the lazy one. So there you don't need to give that the lazy keyword or something like that. So now let's see why the lazy evaluation. What are the benefits of it? The first thing is it avoids the unnecessary computation. As you know, what is this non-strict evaluation? It will be evaluated only when it is needed. That means it can avoid the unnecessary computation. If it is not needed, why should I evaluate it? So that avoids the unnecessary computation and hence gives the performance. Evaluate it only once, right? It's not going to evaluate it 100 times. It's just going to evaluate it once, and that's why again we get the performance gain. And next, and the very important point is the infinite data structure or the streams. This is very, very powerful feature from the functional programming. We are going to look this with example, right? So if I ask you to write a code in a Java which returns the list of all the odd numbers which are present in the universe, what will be the output of your code? Precisely, that will be a stack overflow error, because what we are asking is the infinite list, and due to our hardware and the memory limit, it will give a stack overflow error. But in functional programming, you can do that. you can represent the infinite strings. Of course, with the given hardware, we are not upgrading the hardware. With the given memory or with the given hardware, we can have the infinite list. And we're just going to see how the idea of it, how it is done. We are not going to go into the implementation because, again, if you go into the implementation, it itself is a separate topic for discussion. So we just conceptually understand how the infinite list is represented in functional programming. So what is our requirement is we want the list of odd numbers, right? Infinite list of odd numbers. The way it is done is you create a data structure, right? Where you give the description of what I want. And my description is I want all the odd numbers. So this is how your data structure will look like. It will say I am the odd number, but I am lazy. That means you know lazy, right? Unless it is needed, it won't evaluate it, right? So you have this infinite list with you. This is how you will represent it and you will create the data structure. Since you have this infinite list at your service all the time, what you can say, from that list, give me first 100 odd numbers, right? Then what it will do is, it will go one by one, it will evaluate those lazy elements till 100 and it will give you the first 100 odd numbers. Since that is an infinite list, next time you can say, okay, give me first 1000 odd numbers, right? Then again it will go on that list and it will give you the 1000 odd numbers. But there is one small caveat to it. Can you guess?
Can't call reverse on it. Can't call reverse on the list.
Exactly. And or if you say me, okay, give me the length of this list, right? What will happen? It will start evaluating lazily. It will go infinitely and it will throw stack overflow error on your face, right? So that's the caveat. With this caveat, we can represent the infinite data structures or strings in functional programming language. So though there is a caveat, yet it is a very useful feature of functional programming. So we were looking at what are the benefits of the lazy evaluation. First two we've already seen, and we were looking, now we'll see what is the modularity. In earlier example, I told you, right, whatever is your requirement, that you want the list of odd numbers, you will create a data structure where you will define what is your list is about. In this case, our list is about the odd numbers, right? So you will create the definition in one module or one function, and you will have all the operations on that list in some another module or some another function. That is, operations are get me first 100 odd numbers or get me first 1000 odd numbers. That way you can separate what is the definition of that data structure or a stream and what are the operations which are possible on that list. And that way you can modularize your program. So these are the few benefits of the lazy evaluation or the non-strict evaluation. As he already pointed out, I have already covered that point, that the Haskell, which is a pure functional programming language, has the by default non-strict evaluation, where in Java you have the strict evaluation.
Dina,
Yeah.
can you go 2-3 slides back?
Yeah.
One more?
Yeah.
One more, please.
Yeah.
So here, again, do you want to point out why the println, it's got kind of a side effect here, right? So that side effect is not printed again. So one way to think about it is, again, as Christian already mentioned, aim for pure functions. So if I were actually expecting that side effect to be called, like if I had a database call there or a web service call, that would not be made in a non-strict evaluation. So
By the way, right, why I have shown you this example, right, is to showcase what is the lazy evaluation and not what is the side effect. Of course, in real life, you won't write the code like this, right? But what is important here is to understand the concept. What is the lazy evaluation, right? So, partial functions. Yeah.
One question regarding that modularity. So, sense, we say that make your state and operation encapsulated or in one place. Whereas this modularity says that modular or separate out operations which you are performing with the state. So isn't it a contradictory to what O says or what O philosophy is?
Yeah. So what you are pointing out is to the referring to the encapsulation.
Right.
That is the feature of the O, where you are saying my data and its behavior should be clubbed together, which is not true for the functional programming. It's functional programming is just about the functions, right? And since you just have the functions, in one of your function you will write the description of what the data structure will look like, and you will write the another function where you have all the operations which you perform on that data structure.
When also we have that, for example, collections and the individual stuff, collections.sort, it encapsulates all such operations which are performed on any kind of collection, or the collection repeats. It does have that sort.
Actually, it's a long topic, so it's not that you will always use encapsulation. For certain problems you will use encapsulation. For certain things you will go for functional way of doing it. And it depends on whether, so in case of O, if you have infinite number of types, that means infinite number of possible cases like shapes. If I am having infinite number of shapes, then in that case I will keep my functions within the shapes, but then I will be able to have new types, and all I need to do is implement that functions. But in this case, adding a new function will be difficult because I have to update all the types. Okay. On the other way, if you have, let's say, finite number of shapes and infinite number of operations, in that case I will try to separate the functions from the actual types. Okay, so I have finite number of types. Now in this case, adding a type will be harder because I have to change every function. I have to change every function to make sure that it works for the new type. But adding a new function will be very easy because there are only 3 or 4 types. I just need to make sure that it works for those types. So that's the balance.
And I would actually not really see it as an issue of object-oriented programming versus functional programming, because what you very, very well describe is a question that I have to ask myself independently of whether I go for functional programming or whether I go for object-oriented programming. It's really a question of where do I expect change in my software in future? Will I add new types or will I add new functions? That question is independent of the paradigm. And I also think that the question of encapsulation is not really a question of whether I go for OO or I don't go for OO. If we look at the new functional programming languages, many of these new functional programming languages allow us to mix the paradigms in very nice ways, where and I can also write functional code in Java. Maybe it doesn't always look so nice as if I were writing it in Haskell. And some of the things really get awkward when I try to do them in Java. But many base concepts, like just writing immutable objects, they work very nicely in Java. Just put final everywhere. That's what I do. Whether you really like to do that or not also depends on how you think, whether expressing the final is more important to you or whether terse code is more important to you. For me, in Java, I go for writing final everywhere. At least for variables, not for methods, but for variables. I put final everywhere. And that way I automatically come very close to functional programming. And I can have pure methods. If all variables are final, how could your methods ever be impure? Yeah, of course, they can still be impure if I throw exceptions and such things. And if I do I/O, if I have side effects which hide themselves somewhere else. Yeah, I can still violate these principles, but I will try to minimize that. And for me, this is not contradicting OO and functional. They can actually go very well together.
So just question before, should we do a time check because it's already 9:30? If people want, if they are interested, we can still continue, but it's already 9:30. we should ask audience what they.
We have 16 more slides.
Yeah.
16. It was this is slide number 92. We have 16 more slides.
Yeah, so just let us know. Or we have option. We're gonna have a series.
Tomorrow is off anyways, and besides, most of us get on the waiting list really fast, so we can't postpone this.
How much time do you think it will take? 20 minutes?
15, 20, 15, 20. Yeah. Okay, now let's look at partial functions. That's something which we are discussing in the context of functional programming, because you really should discuss it in the context of functional programming. You should not discuss functional programming without having a look at partial functions, but it's not a problem of functional programming. It's a problem that you actually should always consider when programming. So let's look at this. Yeah. Now we're going into maths, but it's going to be easy. So don't worry doing maths at Friday evening, 9:30. It's going to be easy. It's going to be simple. Yeah. We're even choosing the simplest type of sets that we know of the numbers as natural numbers. N0. That's one for programs. For us, for us, 0 is a real number. For some mathematicians, it still isn't. They don't accept 0 as a real number. But for them, it's a number, but it's very special. For us, it's a normal integer. So let's say f is a function that maps n0 and n0 to n0, which means it takes two arguments of n0 and creates an n0. And yes, even if you say it's too high maths for me, I've written the simple C for you. So you take a U32 and another U32, x and y, and you return a value that's again of U32. And I say it's just the sum of it. So you return x plus y. This is a total function, because you can take any value combination from those input sets and call the function, and it works. So that's a total function. It's defined for all possible combinations of the input values from their types, complete. At least on the left side. On the right side, there actually is a limitation. Can you spot it? What's the limitation on the right side where I didn't tell you the ultimate truth? It's the overflow. It's the overflow. If I call it with 3 billion and 3 billion, I will not get 6 billion. I will get almost 2 billion. It's an overflow. It's not entirely true, but it comes close. Now I'll show you a partial function. And it's very simple. I simply replace the plus with the minus. If I, for example, call it with 2 and 3, you said the return value should be minus 1. But I said it's unsigned. That's a partial function. I cannot call it for all combinations of return values. So this is actually, it has a limitation. It's only callable when x is greater than or equal to y. If I call it with x being 2 and y being 3, my return value would actually be minus 1, and minus 1 is not in the result set. So that is a partial function. And a feature of proper functional programming languages is that they offer support for it, for partial functions. The reason being, as programmers, we simply have to deal with partial functions in many cases. First, I'm going to show you this, which is from the Haskell wiki. This is what you should do first if you have partial functions. You should think again, and you should try to avoid them, because they are problematic. And if you have a partial function, you forget about the fact that it's a partial function, and you call it as if it were a total function, you can actually run in to problems with the program where you say you have undefined states. So now let's look at partial functions in Scala. Let's look at two functions. One function that's called isEven, and the other function is called isOdd. So isEven is a function that says I am a function of int and string, which is if x is divisible by 2, then I return x plus isEven. Otherwise, so the isOdd, same, but yeah, if there's a remainder, it's an odd number. So these are partial functions in Scala. And you can see how to use it. So I can use the collect function, and the nice thing about partial function in Java, I didn't show it on the slide, but you can ask a partial function in Scala if it is defined for your input values. That's what you can do first. Before you call a function, you can ask if it's defined, and then you only would call it if it is defined. Otherwise, you wouldn't call it. In this case, I simply create a list of all the values. So this is how I get the even numbers, and this internally is using this is defined, and also the or else is using the is defined. So in math, I'm using isEven if it's defined, otherwise I'm using the isOdd. So that's partial functions. But I recommend avoid them if you can, as the Haskell wiki said. So if you call a partial function and you didn't check if it's defined, it might bring you into trouble. Yeah, you want to add something?
Yeah, can you go back to one slide?
This one?
Just to clarify, in this case, in the second example, because we are not checking whether x is greater than y, that is why it is partial. The moment I add that check, I think then it's not partial, right?
Well, if I add that check and return a different value, it becomes a total function, because I could call it for all combinations of x and y. And as a Java programmer, what we usually do when we write partial functions or partial methods, we add checks with if, and then we check the ranges, and then we throw something like illegal argument exception or something index out of bounds exception. And actually, that shows you that partial functions are well known to us. Just in functional programming languages, we get totally new ways how to deal with partial functions, and ways which actually are more elegant. If you have a function like in Java, where let's say the square root function for real numbers, and you call it with -2, what it's going to do? For an exception. You can't take the square root of -2 when the result is real. It's another example for a partial function. If you have the square root function and you just define it for the result of real, because then you can't put in an arbitrary real number. You can only input positive real numbers. Because for negative real numbers, you have to return a complex number with I. And so you throw illegal argument exception. So we already deal with partial functions. But in a language like Scala, where you have support for partial functions, you have a variable like x, and you want to know, is it can I actually call square root? You just ask the square root function, can you be called with that? So that's a benefit.
Next slide, please. So how do I convert this to a complete function? Do I say case underscore something?
If the cases would be complete, so they would map all input values, it would actually be a total function. Then you have a partial function object representing a total function. You would actually not do that in Scala. And then you can go for a normal function.
Remove that partial function, Scala compiler will actually tell you that
because it's not exhaustive.
It's not exhaustive.
is the function composition. Again, a very fancy name given to a simple thing. Again, that's a mathematical name and not a computer science name. That's a C program. What it is doing? Output of one function is given as a input to other function, right? And the same thing I can rewrite in this way, right? That's the function composition. Output of one function is given as an input to the another function, then that's called as a function composition in mathematics. So you will say, then why is it so special in functional programming, right? We can do this pretty much in each and every language. We can do that in C, C++, or any language. So why is it so special here? So as you know, this functional programming is all about functions, right? What you do is you write all tiny functions, your functions, and you group or club or compose all these functions together to deliver a bigger feature, right? So that's why the functional programming treats this feature, function composition, as a first-class feature, and it provides you some nicer syntax to do it, right? So that's the definition. Function composition means applying the output of one function as the input to other function. So in Haskell, if you have to do that, they give this syntax f.g. That means the output of G is given to the input as an input to f. By the way, that f.g is a mathematical syntax. In mathematics, if you have to denote a function composition, then you will denote it with this way, f.g. And Haskell has entirely copied this syntax, fully copied this syntax from the mathematics. Assume that you have this list, right? And what you want to do with that list is take one element, call the add function with that element, and whatever is the output, give it to the subtract. If this is what you want to do, then Scala provides you this nicer syntax of and. That space is not required, actually that's by mistake, but Scala provides this nicer syntax where what it will do is, okay, give me a list map. Map means from one value to another, and then what it says is first add, do the addition and then subtract. So language provides some nicer way to do it. That's the only difference of the function composition. And that's about the function composition.
Okay, now about currying. First, where the name comes from. There was a mathematician named Pascal Curry. And you see, the name has been used not only once, it has been used twice. His first name for the programming language, his last name for the concept of currying. And currying is similar to the process of calculating a function of multiple variables for some given values on the paper. So that is what currying is. And let's look at this example where I'm showing you currying in Java. And of course, that's partially correct because Java doesn't support currying, but you can simulate currying with method overloading in Java. It's basically currying for the poor. And so I've taken this example of a complex number and overloading constructor for real numbers with a Aguri method. The complex numbers consist of a real part and an imaginary part. So normally you create a complex number by calling the constructor with two values, with a real value and with an imaginary value. And in currying, I would be able to actually create another function that is calling this function always with one of these parameters already defined and filled. Just like I do here, I say, if I create a complex number, which actually is a real, I only have to specify the real part, and the imaginary part is fixed to 0. That's explaining the feature of currying to you without actually using the feature of currying, but I've used the feature of method overloading to simulate currying. but I think that demonstrates quite nicely what this feature is used for. And there's a formal definition. If you have a function f that takes two, or you could also do it with more, input sets and creates an output set, and currying makes it a function where you actually map x to y to z. So that is curry f takes an argument of type x and returns a function of y to z. So x is already specified. I actually did it not really with x, I did it with y, but that doesn't really matter. So here's an example of how to do currying in Scala. And this now also demonstrates to you how it looks like if you actually have proper support in the syntax of a language for currying. So we have a function named add. So this is the example without currying. We have a function like add, and it takes x and y. So we say this x plus y. Simple. And if you call it add 1, 2, we get 3. If you call it add 7, 3, we get 10. I think that's obvious so far. Now let's look at the example when we use currying. When we use currying, we actually write functions in a slightly different way. We write the functions as if they're function of function. So you now just basically replace the comma with closing the brace and opening it again. Let's say x plus y. And then I call it like this, add 1, which then returns a function which is 1 plus y. And then I call that function. So in the first call I have replaced x, and the second call I have replaced y. And that's basically curry. Yeah, that's a question.
So, what exactly is the benefit of having curry over here? Means, if we have function, a pure first class function, who is taking two arguments and summing up them, what exactly currying is value adding over here?
Actually, there's I can think of more than just one benefit of currying, but let's assume this is a more complex calculation. Currying can help you in doing a partial calculation when actually you have two input values, x and y, and in your use case, you only use a small number of different x values, maybe just one, but a large number of different y values. So you can use currying for pre-calculation. Right? You don't do the pre-calculation itself. The concept of currying and a runtime environment supporting currying is performing the pre-calculation for you. Because this actually, until here, pre-calculates the function for you. That's what currying is for. And the other, I can think of the perspective of reuse in similar situations when an object-oriented programming languages actually it's not really a feature of OO. It's just a feature that usually comes with languages that support OO, where we use method overloading, where you say you have various parameters and sometimes you just default them. And currying supports that you basically default parameters yourself instead of having the predefined versions.
Yeah. So can we utilize the currying to add 3 or 4 numbers as well in the same statement?
Not only one statement, but you could store the result of add 1, and that would be a function that then adds 1 to another number, and then you could call that function multiple times. So that's basically the idea behind the currying. Okay. Dina, anything you want to add to currying?
Yeah, so one more benefit is the time inference. We've covered time inference.
Not really.
Scala, not specific to any.
So for Haskell, you don't need that. Haskell is.
Okay.
So one benefit here, let's say in case of add also, let's say I want to define a variable that says add 1, and I can call only add with 1, and whatever x is there, y is there, I am not providing that that variable. and then what I am doing is I have a list and I want to add 1 to every element of that list. In that case, I can say list.map and pass in that new function that I have partially created. So I have said that what I want to add, but I haven't said that in which element I want to add. So in that case, I am taking that from the list and I am adding 1 everywhere. And that way you can create different versions of that and you can add anything you want.
I also have an example of how to query existing functions. It's also something that you define in languages like Scala. So we again have the add function, but now instead of creating a queried add function myself, I tell Scala, I have this unqueried function, please query it for me. And then I can call this is how I call the unqueried function, this is how I call the queried function. It again has a mathematical background. There are certain mathematical concepts of reasoning which can only be meaningfully applied to functions that only take 1 argument. And querying helps you to reason about functions that take multiple arguments by turning them step by step into a function that only takes 1 argument. Okay, I think that's it.
Yeah, just one note that as promised in our syllabus of a talk, we said that we will be covering the pattern matching, but we are not covering it for the 2 reasons. A, due to the time constraint, and B, in one of our future expert talk, we are going to cover the algebraic data structures. And the concept of algebraic data structures cannot be completed without the pattern matching. So we are thinking that we will cover the pattern matching as part of that talk. Just to. So yeah, that's it from our side. If you have